A very good day I bid to our SEDEX panelists. My name is Kim Boon Kim from Pressure Engineering, and I'll be presenting on my FRP topic on molecular simulation of methane and surfactant VES sorption on Kerogen. And the discussion for today are as outlined according to the FRP format. We will start off with some brief introduction on the project and all the way to the conclusion at the end. First of all, for introduction, the project revolves around shale gas reservoir as we are trying to relate Kerogen in the bigger picture. The things that we should know about this shale reservoir is that it is an unconventional reservoir. Shale is usually part of fracturing system, which is the source rock. Here, we're trying to go to shale itself to extract oil and gas as if it is a very good hydrocarbon storage. A process known as hydraulic fracturing will be implemented to frack the shale to create a conduit in order to increase the permeability of shale to extract the oil and gas, as the typical permeability of shale is not that high. As for the problem statement, the first point suggests that there is an issue when it comes to the ease of release of gas. Based on research, adsorbed and diffused gas holds up to about 20 to 85% of the gas stored in shale gas reservoir, while free gas accounts only about 30 to 47%. So to produce more gas in the long term, there should be a focus on adsorbed and diffused gas, of which in our case, we are simulating the adsorbed gas. Secondly, I believe we do understand on how surfactant works on a macro scale, reservoir scale level. Here, we include surfactant to study its effect on a nanoscale level through molecular dynamics simulation. Lastly, we are trying to look into how realistic our simulation is as compared to the macro scale level. It's about how we can correlate the nanoscale to the macro scale level. When it comes to objectives, we are trying to understand how surfactant affects the sorption behavior of methane and shale, and that can be further explained by the deviation of methane in the system through the root mean square deviation function, which I will talk in the results section. We also introduce a few parameters which are salinity and pressure to investigate their relationship in the adsorption of methane. The scope of study includes three main components, namely the shale, hydrocarbon gas, and fracturing fluid, which are represented by graphene, methane, and surfactant respectively in the simulation. The usage of graphene and the type of surfactant, which is used in the industry as viscoelastic surfactant, CTEP to be exact, are supported by several papers. And the methane is used as it is the component with the highest percentage present in shale gas. The principles behind any molecular dynamics simulation are these two equations, Newton's second law of motion and the potential energy function. From Newton's second law, we can identify the acceleration of the particles, as we know the mass of each particles of all the components, and force from the net gradient of the potential energy, which is converted into kinetic energy, thus the acceleration. From acceleration, we look into its velocity and trajectories, which is the displacement of the particles. That's what we are interested in, the adsorption of methane molecules. I'm putting up only some of the literature review as an example, as we have about 30 papers to provide input for the project. The first paper from Gandersi helped me to understand on viscoelastic surfactant application as fracturing fluid, while the second paper provided me a general overview of shale gas reservoir. The third paper here suggested me with the application of CTEP as surfactant used in VES. Enters the methodology. Here are the few software used. GROMAX is used for the molecular dynamics simulation. Avogadro is used to create the unit cell for methane, graphene, and surfactant. VMD for visualizing the system at every stage of simulation, and QT-GRACE for graph plotting and analyzing for the results section. Here are the 9 steps of methodology. It goes from developing the whole molecular structure, developing IPP files, which is the parameter file for each component, generating topology, which is the parameter for of the system, building up simulation blocks, adding molecules, and solve it because our fractional fluid is water-based. Also, neutralizing it, energy minimization, equilibration, production MD, and lastly, analyze the result. I will be explaining all of them step by step next. In building the structure, we are using CHAM36 FORCEFIELD, which is the best source field to be used in the investigation of methane in shale according to literature review. Graphite unit here will be combined into graphene slabs, which will represent the shale layer, CTEP or cetyl-trimethyl ammonium bromide as surfactant, and lastly, methane. They are all generated from Avogadro itself. In terms of modeling setup, I investigated two systems which are pure methane and methane with CTEP, the viscoelastic surfactant. Both the systems are simulated under 4 environments each, which are from the combination of low and high salinity with low and high pressure. In terms of salinity, 0 mole per liter is used for pure water system, and 1.0 mole per liter, which is about 35,000 ppm, for high salinity when it comes to a reservoir system. As for pressure, 1 bar is used for low pressure system, which is under the atmospheric pressure, and 150 bar for reservoir pressure of about 2000 plus psi. As for parameter of the system, box dimension of 2.5 nanometer is used for X and Y axis, and 4.5 nanometer for Z axis, which represents the thickness of micropores of the shale layer, which contributes to the adsorption of methane. Safety margin is introduced, 2 steps of graphene sheets are prepared, which I will show later, 100 molecules of methane for consistency. As for CTAP, 20 molecules are used as it agrees with the CMC, critical missile concentration of CTAP, according to Belhaj et al. Reservoir temperature of 125 degrees Celsius were fixed, and the salinity variation are as shown below. Here is the modeling setup for pure methane system, where we first built a simulation box with slabs at the top and bottom. As you can see from each slab, there are actually 2 layers of graphene sheets. This is important to know whether our methane is actually diffused or adsorbed. If it is diffused, then it will be in between the 2 layers. If it is adsorbed, then it will be outside but close to the slabs. If it is free gas, then it will be in between the 2 slabs, in between as shown in the middle image. Here we introduce methane and water to the system. When it comes to the system with methane and surfactant, it is similar to the pure methane system with just an additional inclusion of CTAP from the third image. The next step is neutralizing of system, which is important because nothing in nature can actually be present with charge as they are unstable. From the first picture, there is no ions added as it is just a pure methane system. The second picture of 1.0 mole per liter salinity contains 20 sodium ions and 20 chloride ions, which are grey and purple respectively. Sodium chloride is used as a salt in this stage. When there is inclusion of CTAP, which is cationic with the charge of +1, an additional of 20 chloride ions are introduced to neutralize them, as can be shown from the third and fourth image. This is the final modeling setup before running for simulation, where high and low salinity are defined for pure methane system and a system with inclusion of CTAP. As you can see, all molecules are relaxed in such a way that they are all confined in the box itself. If there are molecules outside the box, that will simply mean that the simulation might be inaccurate. When it comes to energy minimization stage, our total force of the model should not exceed 1000 kJ per mole nanometer as standard in the molecular dynamics simulation. This will prevent direct clashes or inappropriate geometry when they are in the naturally stable condition. When it comes to equilibration, we include position restraint to graphene to prevent them from moving, because shale do not move in the reservoir. The 2 ensembles defined in this simulation are the isothermal isochronic NVT ensemble, where the number of particles, volume, and temperature are held constant, and the other is isothermal isobaric NPT ensemble, where the number of particles, pressure, and temperature are held constant. The 2 pressure used were, as aforementioned, 1 bar and 150 bar. The production MD stage denotes the final stage of the simulation. As can be seen from all images, there are no methane present in between the slab layers, which means there are no diffusion occurring. The adsorption of methane is apparent as the methane molecules are moving close to the graphene slabs. These 4 images are the simulated models for pure methane system under the combination of high and low salinity with high and low pressure. The same explanation here for the system of methane with CTAP under the combination of high and low salinity with high and low pressure. When it comes to the result section, these are important to ensure that our model achieves the intended environment. All models have temperature of 398.15 degrees Kelvin according to the average line. When the simulation is intended for 1 bar, the average line is at 1 bar and the same goes for 150 bar. This gives confidence in our model that they are simulating accurately. In radial distribution function, in both graphs, the black line represents the methane distribution in pure methane system, while the red line represents the methane distribution in system with surfactant. As you can see from the center of the simulation box, the red line shows higher reading, which means more methane is under the free gas state with the addition of surfactant. This would simply mean that the adsorption of methane is reduced with inclusion of surfactant, as it reduces the IFT level of methane towards the graphene slabs. The same applies for both high and low pressure under low salinity. And the same thing applies for the system with low and high pressure with high salinity. Root mean square deviation is where we can see a clearer picture of how the displacement of methane works. The horizontal average line shows the deviation of methane from its original position towards the graphene slabs, where higher reading means closer to the graphene slabs with higher adsorption rate. As it can be seen from both low and high salinity with high pressure system, the red line reads a lower RMSD value, which means that the affinity of methane adsorption is lower than surfactant is present, and that means more free gas in the system as compared to the pure methane system. When it comes to pressure, it relates to the solubility of methane in the system. When it is pure methane system, the red line which denotes higher pressure has higher reading, which means higher adsorption. According to Henry's law, higher pressure allows more gas to be dissolved in the solvent. Higher solubility can be translated to higher kinetic energy of methane for adsorption to take place. However, with the inclusion of surfactant, the higher pressure allows the surfactant CTAP to dissolve better, and it helps in the reduction of interfacial tension of methane to graphene slabs. When it comes to salinity, it relates more to the electrostatic forces. Given that the methane itself already has low solubility in water, the inclusion of ions from salt further reduces the solubility of methane, thus slowing the displacement and adsorption effect of methane. On the left, it can be seen that the difference for high and low salinity is not that much for the deviation of methane, but the deviation of surfactant CTAP is definitely higher in a high salinity system, as can be seen from the right picture. This is because the polar components of the surfactant react with the valent ions of the salt to produce complex ions, and this permits a better dissolving rate for surfactant and subsequently reduce the interfacial tension of methane towards the Kerogen structure. The final result here shows the deviation of graphene from its original position. As can be seen, there is only minimal movement of graphene slabs of less than 0.015 nanometer as the position restraint holds them in place throughout the simulation. If the graphene slab moves around too much, the whole simulation will be inaccurate. In conclusion, CTAP is actually effective in displacing methane out from the micropores and mesopores of shale. Also, we have analyzed the effect of salinity and pressure with and without the presence of surfactant towards the adsorption of methane. Lastly, these inputs will help to provide more information for optimization purpose in future production. When it comes to recommendation, it is possible to scrutinize the effect of salinity and pressure on a wider range. Also, using a more specific Kerogen model. As for this project, I am using graphene model, which is more of a generalized approach. Lastly, we can also include cost factor into consideration.